Alright, so in this lesson, I will be showing the different types of transformations that you can apply to trigonometric functions. So to start with, let's write the base equation for every transformation included in their variable state. So let's just start with y equals AF k x minus d plus c. So this is what it would look like for a normal function, but for trig, it's just a little bit different. So for trig, it's still y equals a, and we use sine as the base trigonometric ratio. However, the sine could be replaced with either cos or a tan or whatever ratio you're using. So I'll just keep those down there. And then it is k. And now this could either be theta or x. The actual variable doesn't really matter too much. Some people use theta, some people use x, depending on the question or something else. So I'll just switch to x just to make it a little bit easier. And then still minus d plus c. So the transformations in trigonometry compared to the normal functions, for the most part, are pretty similar, with a few differences. So to start with, let's start from the left side of the equation to the right. So we always start with y equals. And then we have our first variable, which is a. I'll just circle that in this. So a is our first transformation. So a is going to be your vertical stretch or compression. So the a affects the y value, meaning if a is greater than 1, it's a stretch, and if a is less than 1, it's a compression. Now, another way to think of a is a for amplitude. So the a is actually the amplitude in a trigonometric function. So if I had a function such as, let me just switch back to black. So if I had y is equal to 4 sine x, let's say, this 4 here, because it's in front of the sine, it is going to represent the amplitude. Meaning, if I were to draw a graph, now a normal sine graph, if this was 1, -1, let's say you have your, whatever, pi over 2, have your pi, 3 pi over 2, 2 pi. So a normal sine graph would be looking like this. This is your basic sine x graph. But with the 4 added to it, the amplitude, because now it is 4, that means that the max point is 4, and the lowest point is -4, because now all the y values get multiplied by 4. So 0 stays 0. The 1 gets multiplied by 4, so it goes up to 4. 0 stays 0. 1, or -1, sorry, gets multiplied by 4 to become -4, and then 0 stays 0. So the new function would look like this. And that affects the vertical stretch or compression of the function. All right, so for our next part of the equation, we have our k value. So the k value, it's going to determine your horizontal stretch or compression. And the k value is different compared to the amplitude in the way that if the k is more than 1, then it's a compression. But if it's less than, if it's less than 1, then it's a stretch. And it affects the x-axis. So if I had a graph, let's say, and then I had, let's say, y is equal to, let's just do base stuff. So let's do sine of 2x. Then my sine graph, so if I have 2 pi over here, which is normally 1 cycle, then because it's 2x, that means all my x values are divided by 2, which means that my 1 cycle is going to actually end at pi. So if I were to graph this, it'd probably look something close to that. So it gets compressed by 2, by a factor of 2. And the k value and the period also go hand in hand, because you can find one if you have the other. So let's just do a bit of examples. So the formula for finding them is p, which stands for period. So p equal period. So p is equal to 2 pi over k. And k is that value that is in our equation. And then we can also, if you do some cross multiplication, you can also say that k is equal to 2 pi over a period. And the way we would use this is if, let's say, a question asks to find the period of a function and you have the equation. So let's say they say k is equal to, as an example, 4 pi, let's say. And then you need to find the period. Well, you can use k is equal to 2 pi over period. And your k is 4 pi, so you plug in 4 pi is equal to 2 pi over p. That means the period is equal to 2 pi divided by 4 pi. So we'll just go back up here. So p is equal to 2 pi over 4 pi. So p is equal to 0.5. And then the same thing can also be done the other way. So if they say that the period is 2, then you can find your k value if you plug in 2 for p. So you can have 2 equal 2 pi over k. That means k is equal to 2 divided by, 2 pi divided by 2, which is just equal to pi. So that's your main horizontal and vertical stretches and compressions. And we also have, let me just get rid of this. We can also have a reflection over the x or y axis. So the way that that would look would be a negative value in front of the amplitude. So if we had y equals, let's say, negative 2 sine x, or it doesn't even have to be a number there. It could even be y is equal to negative sine x or cos x or tan x. If we have our graph, let's take negative sine x as an example. So a normal graph of sine would simply look like this. Okay, I'll mess that up a little. But that would be a base sine graph. Now, if we apply the negative in front, it's going to be a reflection over the x-axis, which means the positive numbers become negative and the negative become positive. So 0 stays at 0. Switch to yellow. 0 stays at 0. 1 becomes negative 1. 0 stays 0. Negative 1, which is this thing, moves up to 1. And then the other number stays, so 0 stays 0. So it would look something, even though it's wonky, it would look something like that. Now the next thing we have is our phase shift, which is our d value. And I'm just going to quickly redo this in yellow here. Okay, so our d value is our phase shift. And what the phase shift is it's basically horizontal translation. So assuming we had translation. So assuming we had a function y is equal to the cos of, let's just say, x plus pi. What this would mean is if we graphed our cos function, if we had our base cos function, the plus pi means it shifts to the left by 1 pi. So if the full cycle is 2 pi, and half of it here is pi, and we extend our graph, then that means the new graph, every point will have to shift back a pi. So let's say this is negative pi here. That means this point at 0 will go back to negative pi. This point, if that's at, let's say, pi over 2, that's going to go back a pi. So we go to negative pi over 2. Pi, this point here, will go back to 0 on the x-axis. 3 pi over 2 goes back to pi over 2. So this point here will be shifted back to here. And then our 2 pi will be shifted back up to pi. And then that would be our new cos function. So it's always going to be the opposite of whatever the sign is in the brackets. If it's plus something, it moves back. If it's x plus something, it moves to the left. If it's x minus something, it moves to the right. So now, with that being said, there is one thing to be wary of when doing graphs like these, or equations, I should say. And that is, sometimes you'd be able to factor out a k-value from inside the brackets. So what that would look like would, let's say we had an equation that says y is equal to sine of, let's say, 2x minus pi, right? We can factor this in the brackets, right? Some people would see this and they would just think, oh, okay, that means it's 2x, which means the function gets divided by 2, and then a minus pi, which means it shifts to the right by pi. But that actually doesn't work because we're able to factor out from the brackets. So what that would look like, the new equation, would be y equals sine, and then we can take a 2 out. So sine of 2, and now you just factor the 2 out. So x minus pi over 2, because you're dividing the negative pi by 2, so you get negative pi over 2. So now you can see the difference. So the 2x is still kind of the same, you're still compressing the function by 2, but instead of moving to the right by pi, it moves to the right by pi over 2. So that's one thing to be careful of when doing equations like this. And now the last thing just to watch out for is the c value, which is at the end. Now the c value is just your vertical translation up and down, and this is actually really simple. Now the vertical translation can also be seen as your axis of symmetry. So to do a little example, let's say we have y equals cos x plus 4. So our plus 4 is our c value. And if we were to graph, so let's do our basic cos function. So this is the base cos function. Let's say 1, -1. If we have a plus 4, then that means every point will shift up by 4. So let me just fix that. So we'll have 1 will go up by 4, which means the highest point will be 5. Our highest point would go up to 5 because 1 plus 4 is 5. Our 0 will go up by 4, so it'll become 4. Our -1 will go up by 4, so it'll become 3. and then our 0 goes back up to 4, and then our 1 will go up to 5. And that is your new coast graph, which is going to be every point 4 higher than the original. And if you try to find the axis of symmetry on this, so if you remember, the axis of symmetry is equal to your y max plus your y min over 2, then that would be equal to 5, because that's our max, plus our minimum, which is 3 over 2, which is equal to 8 over 2, which is equal to 4. And this 4 is the same value we have as our c. So the axis of symmetry is the same as the c value, which is going to be your vertical translation by however many units. And one last thing to note is there isn't really a reflection over the y-axis. That doesn't really work with periodic functions like this all too well. Sometimes they're used, but most of the time they're not going to be used in situations like these. So it's nothing really to worry about. But if it ever did appear, then it would be a negative value before the x or before a k value. So let's say negative 2x or just negative x. And then that means the function would be flipped the other way. So kind of imagine flipping it like a book over the y-axis. And that is basically everything to know about translations. In the next video, I'll show how to how to find an equation from a graph. I'll do a couple examples on those. And then the video after will be showing how to make a graph from an equation.